right, this is our test walkthrough for our Q3 test for statistics. So to start off here, our first question, we read through it and we know that we have random sample of 35, and we have a mean or an x-bar of 34.7 and a sample standard deviation or S of $4.85. So we're looking for a confidence interval. So the first thing that I note here is I have a sample standard deviation. So that means that I have an unknown sigma. So I'm going to pull out the calculator that is for an unknown standard deviation. If I knew sigma, then I would want my known standard deviation one. So I can go and fill out the info that I know here. So my x bar is 34.7. My standard deviation, my sample standard deviation is 4.85. My sample size is 35. Okay. So the last thing that I need is my critical values. So that's my T sub C. So for that, I'm going to need my T chart. So if you go to our T chart here, I'll hop back over so you can see it a little bit larger. Here, I have a sample size of 35, so my degree of freedom is going to be one less than that, or 34. So if I hop down here, well, I don't have a 34 here, but so I always go down more just to be safe. So here's 30, and I'm looking for a 90% confidence interval. So if I have my 90 column, go down this column to my 30, and I get 1.697. That's the one I'm going to be using. I'll go ahead and circle it because this is a disposable one, which I recommend you draw all over yours when you get it on your test. So if I input that over here, that is 1.697. So then we get our confidence interval here. So that if we round it, is going to be between $33.31. And since we're doing dollars, we're going to do that to two decimal places for cents, because that's how we typically do work with those. Our mu is between that and 36.09 if we round it dollars. Right? So there we go. Now the second question is user answer from part A to estimate the range of dollar values for a total sales in one day if she can sell to 25 clients in a day. So this is kind of asking you is like your kind of worst case and best case scenarios here. So if I sell to 25 people and I have the worst possible sales for each person, which is going to be 33.31, that's me getting 832.75. So the low range there would be $832.75, and then the higher range for my mu of 25 being sold. And then my upper range is going to be that same idea, but 25 times 36.09. And that gives me 902.25. So if I sell to 25 people per day there, I would expect to have a sales range between there and there for each of those days. All right, hopping down to part 2 here. So we have a random sample, and we're trying to find a 95% confidence interval for this one. So on this is going to be the same test as we just kind of had, right? So if I hop over here, get rid of all this, right, my x bar I don't know yet because I would have to find the actual x bar of that data. Sample standard deviation, again, I don't know that either. I'm going to have to find that. Sample size, I do already know that. I got 1, 2, 3, 4, 5, 6, 7, 8. And then I'll have to, then for my critical value, I'm looking for a 95% confidence interval. And then I have a sample size of 1, 2, 3, 4, 5, 6, 7, 8. So one less than that is 7. So go to degrees of freedom. Here, I'll show you this. Degree of freedom of 7. Looking for the 0.95, and that would be 2.365. for that one. So back over here to, there we go, 2.365. All right, so now we need our x bar and our sample standard deviation. Well, we should have your standard deviation calculator as well. So I'm going to go ahead and clear out all this. I'm going to input that data into that chart. So we're going to have 27, 38, 30, 42, 24, 37, 30, and 39. So that gives me an x bar of 33.375. So we'll input that. And we had a standard deviation of 6.457. You can take those decimals out as far as you want, but 3 or 4 places is typically going to be fine. So then click off of it. Then there's our confidence interval. My confidence interval, if I round that off, is going to be 27.98. These are measured in minutes. And my upper bound is going to be 38.77 minutes. So there we go. Unit-wise, I'm not going to be a big stickler on that. It's a really good habit to be in, but I'm not going to ding you points for not putting the appropriate units there. But do try and have it written in this kind of format for me for the lower and the upper bounds there. All right, we go down to number 3. So we have a random sample of 78 students. 59 said that they would vote yes for sharing the money for their treasurer. So this is going to be a proportion test, right? So you need to find a point estimate for P, a point estimate P hat for P. So that is going to be the super easy one. That's just our number that said yes out of our total that we surveyed, which is 78. And if we go and estimate that as a decimal, 59 divided by 78. 0.7564. Is my p hat value, or at least my estimate for it. So now for B, we're trying to find our 90% confidence interval for P. So we're going to have to go back over to our calculators. We should have a confidence interval for P. Did we get these in the right order? Yes. Okay. So our number of successes, in this case here, is 59. Our sample size was 78. And then we need our critical value here. So this is a Z sub C, so you should already have your chart in it, which is why we put it there. We're looking for a 90% confidence interval. So for 90%, I want this 1.645, which I already have in there. So there we go. So 1.645 gives us this as our upper and our lower bounds. So my lower bound is 0.6765. And this is estimate for P, not for mu. And then our upper bound is 0.8364 if we round it. So again, on this one, there's not really units. We're talking about probability because it's just it's a decimal, it's a probability. There's not a title for it. So you can just kind of leave those without those units there. All right, there's our first page. So let's hop over to page 2. And I will say that these are in order. So if you're looking in your notes, early stuff is probably from chapter 7, then middle stuff is chapter 8, last part is chapter 9. That should hopefully help you out. I try and keep that in order so you guys aren't going crazy back and forth throughout your notes. It might not be in order of like 8.1, 8.2, 8.3, 8.4, but it is going to be all of Chapter 7 stuff, then all of Chapter 8 stuff, then all of Chapter 9 stuff. Okay, that being said, here to part number 4. So I'm trying to test which batteries last longer. So we have one brand. We have a sample size and an X bar for that brand, and then our other one we have a sample size and an X bar for that one there. Historically, we have found that the standard deviations are 2.2 and 3.5 respectively. All right, so this is going to be a difference in mu, right? Because we're looking at the difference in the averages here. And we have known standard deviations. We know our standard deviation for sample 1 and for sample 2. So go to my calculators, and I want my calculator which does confidence intervals for a difference in mu with a known standard deviation. Again, if this was when it was unknown, then I would want to say it was S and not sigma, then I would want my unknown standard deviation. But with this one, I can use this calculator here. So clear out all this stuff, and then let's start to put things in. So our X bar 1, so I've conveniently labeled these as 1 and 2 for you. So we're going to have 9.8. And then my sample size, my N1, is 42. And then my sigma 1 was 2.2. My X bar 2 was 8.1. Sample size of 38. Standard deviation of 3.5. Then my critical value, which I'm looking for a 90% confidence interval. So 90% is going to be 1.645. I'll scroll back over. I made it bigger just so it's easier to see on your guys' screen. When I do that, I end up with 0.6118. As my lower end there. And then my upper end for the difference in our mu's is 2.788. I need more, doesn't want 2. There, now I have 4 on each. Okay, so there is my difference there. So again, our calculator can kind of help us out with doing basically all of that part. So then on part B is a little bit of an analysis problem. So I'll hop back over so you can see that a little bit larger. Does the confidence interval contain all positive, all negative, or both positive and negative numbers? What does this tell you about the mean life of battery brand 1 compared to battery brand 2? So ours are both positive here. So if it's positive on both ends, what I'm saying is I'm confident, 90% confident that the actual value of M1 minus M2 would give me a positive number, meaning that the average, or M1, is larger than, that mu1 is larger than mu2. Okay? Because I'm only getting positives when I subtract them. So that's what I would be saying. Hey, I'm confident that mu1 is larger than mu2. If I had all negative, so negative here and negative here, that would only happen if mu2 was a larger value than mu1. So that's what I would get there. If I have a mixture, so one of them is negative and one of them is positive, then I don't have enough evidence to kind of say one way or the other, because I'm kind of right there in the middle. So since I have all of that, so they're both positive, that tells me that brand 1 seems, because we don't want to say words like is, because we are not certain, because we're 90% confident, seems larger than brand 2. Again, I'm not going to be like crazy picky about your language, but it is a really good habit to be in, as far as just trying to always say what you can say and not try and overstep the things you can or cannot say. All right, down to problem 5 here. So a furniture store getting a new campaign. So they had a long-term average sales each day of $24,819. So they did a random sample of 40 days during their new ad campaign, and that gave them a mean of $25,910 per day. So is this enough evidence to say that on the 1% level of significance, that the campaign worked effectively, right? So, and we were told that our historical standard deviation is 1,917. Okay, so this is a hypothesis test. So this is one of the kind of longer ones. First thing I'm going to do is state my null, my alternate, and my level of significance. So my null here, which is going to be my H sub naught, is that my mu has not changed. Is that my mu is still $24,819. Okay. My alternate, H sub 1, is I'm specifically in the problem saying that I believe my sales worked, my ad campaign worked. If I just look at, hey, did it have an effect? Then I might say not equal to, but hopefully your ad campaign increases sales. It hopefully won't make your sales go down unless you have really, really bad ads. So I would say that my alternate is that my mu is now larger than what it was, which was $24,819. So there's my alternate hypothesis. And then my alpha, I'm at a 1% level of significance, so that's going to be 0.01. All right, so should I use a standard normal or a student's t? Well, I'm told sigma, right? So sigma means that this is from the population, it's not from the sample. So I have a known standard deviation, so I can use the standard normal, which is the z1, right? If you ever forget, your calculator should have z or the t on the appropriate one, so you always kind of check there. But this is standard normal, which means I'm going to be using a z for that one. Right? And then we need to calculate what the z is. So there's where we actually need to do a little bit of math here. So our equation for that is x bar minus mu over sigma divided by rad n. So I'm told basically all of this information here. So my x bar is 25,910 minus my mu. I'll do this a little bit more. I'm kind of going off the side here. My mu is 24,819, right? Divided by my sigma, which is 1,917, divided by rad of n, and my sample size was 40. So kind of a mess, but all I really got to do is go to a calculator and type all of that in. So let's do it out. I will do 25,910 minus 24,819. That gives me a top of 1091. So I want that divided by 1917 over the square root of 40. Again, you can do this all in one massive step. I typically try and break it down a little bit by a little bit just to kind of be extra safe, because it's really easy to make a little error with parentheses and stuff like that. But we end up getting 3.5994. So z equals 3.5994. All right, so now for C, we're trying to find our estimate for our p-value. So for that one, I just had a z. So when I go to my chart, I don't want my t-chart, I want my z-chart. And it should be clearly labeled for us. So I have a z of 3.599. I might call it 3.6 0.60 if I'm going to be rounding here. So 3.60 is off of our chart here, right? And when we're off the chart, and this isn't going to happen on the actual test. This is just I picked some bad numbers for this practice test. We're beyond the chart, so we use effectively 1 for all of this, right? Or 0.999 repeating, which is just 1, right? But let's say that it was, for the sake of showing you this process, let's say that it was 2.599 or we'll say 2.59. Sorry, 2.59. Here's 2.5. Go over to the 9. And we have a 0.9952 as our p-value there, right? So since we have to estimate it, we would say that our p-value is, since we're greater than, we got 1, right? But that is for a left tail, right? So we're way over here and said, hey, everything left of it is 1, which means everything to the right of it is effectively 0, right? So 1 minus 1, super easy math for you, gives you a 0 for your p-value, right? It ends up being, if you do the actual calculation without the estimate chart, like 0.0001. So it's a very, very small number, so that's why we're estimating it to 0 there. All right. Then for D, based on your above answers, do you reject or fail to reject the null hypothesis? So 0 is less than our alpha of 0.01, right? Which is why we really don't care about the exact values, because as soon as I'm off the chart, I know it's going to be rejecting the null. So I'm less than my alpha, I reject the null. So I will reject the null at 1% level of significance. Because our alpha is greater than our p-value. Right. So that's what I'm kind of looking for as far as that goes. I don't need some grandiose explanation of what it is. All I really want is purely just so that you're not just saying reject or fail to reject as a kind of 50-50 shot. I want you to explain why you do it, so I know that you know when to reject and when to not reject, at the very least there. Okay, on to the next page, problem 6. Okay, so we have a telemarketer is trying 2 different sales pitches, one that is aggressive and one that is a little bit more passive. So on this, you did 175 and got 62 that were successful. And on the other strategy, he did 154 and got 45 that were successful. So does this indicate that there is a difference in the proportions of sales for buying the service? And we're going to use an alpha of 0.05. So again, we have another hypothesis test, but this is a difference in proportions. That's why I'm kind of specifically saying the term proportion when I'm writing these, right? So our null is going to be that the difference is 0. So our H sub naught is that our difference in P, so P1 minus P2 is 0. Meaning, hey, there's no difference in sales pitch, people just buy it or they don't. Our H sub 1, which is our alternate hypothesis, we're trying to say, hey, is there a difference? Because I'm not trying to say, hey, aggressive is better or passive is better. I'm just saying, hey, it doesn't even matter, right? So that's going to be that P1 minus P2 is just not 0. Okay. And then my alpha is 0.05 in this case. So then is this going to be a standard normal or a student's t? Explain why. This is going to be standard normal. Our proportion tests give us z's. And again, if you ever need, just look at your equation for it. Is it a z or a p, or sorry, a z or a t equation? And this one is a z. So it's going to be standard normal. And you need to find our z. So to find our z, we first actually need to find our p bar. Our p bar is r1 plus r2 over n1 plus n2. And that is effectively the total yeses over the total for everything, right? So our total yeses would be 62 plus 45, which is 107, over our total, which is 175 plus 154, which is 329. So if we do that as a decimal, because you probably don't need it as that ugly of a fraction, 107 divided by 329, we get 0.3252 as our p bar, and meaning that 1 minus that, our q bar would be 0.6748 if I round it. Okay, so now that I have those, I can find my z. So my z here, if you recall, is going to be my p hat sub 1 minus p hat sub 2 over p bar q bar over n1 plus p bar q bar over n2, all square rooted. So again, kind of an ugly bit here, but all of the bits we already have somewhere here. I do need to write down what my p hat 1 and p hat 2 are, so I'll do that kind of over here. Sorry, I'm a little bit crammed on space here. So p hat sub 1 is going to be 62 over 175, 0.3543. And then my p hat sub 2 would be 45 over 154, which is 0.2922. So I have all the bits that I need. All I gotta do is some plugging in. So again, I recommend doing it little bit by little bit. So I'm gonna do my P1 minus my P2. So that would be 0.3543 minus 0.2922. So that's going to be 0.0621. So top of my fraction is 0.0621. And if I do that entire bottom part here, p bar times q bar is 0.3252 times 0.6748. Divide that by N1, which was 175. And I get that. If I then add that to point 2194446. That's just my p bar times q bar from earlier, right? Just trying to save up a little bit of work there. Divided by N2, which is 154. So I've now added those two things. And then when I square root it, I get 0.05176. So if I divide those, 0.0621 divided by 0.05176, I end up getting 1.1998. So there is my z. Now to find p, since I have a z, I'm going to go to my chart once again. Sorry, my z 1.199, 1.1. If you do 1.199, we're actually going to be rounding that to 1.20. So 1.20 is actually right here, 0.8849. Okay, but once again, that is on the left-hand side, right? And I'm looking for stuff on the right side of it. So I need to do 1 minus that. 1 minus 0.8849. I get 0.1151. But this is a two-tailed test, right? So that just tells me the right end of it. I also need the opposite side, the left end of it, which is going to be, it's that times 2. Because I get 0.2302. For my final p value on it. Okay. So then on D, do we reject or fail to reject? So here my p-value is larger than my alpha. Okay, so I'm going to fail to reject. At 5% level of significance. Since I have an extra letter in there. Okay. Since our alpha is less than our p-value. Right. And again, the reason why I want that explanation is so that even if you make a mistake here, I can still see here that, hey, you know how to end this, even if it is incorrect work above it. Okay, and so again, sorry about the room. I tried to come on as few sheets as possible. You will have more room on the actual test. I promise you that. Okay, so number 7. So a pizza restaurant advertises that they deliver in under 30 minutes. So we do a random sample to test that. Based on the sample, we get these data points. We're trying to test it on a 5% level of significance. Okay, so this is going to be another hypothesis test. So we're going to be testing mu here. The difference is we have a sample as opposed to me just kind of giving you the values. So our null is that the mu is 30 because they say, hey, we want to deliver in under 30 minutes. So we're just going to say, hey, let's say they do deliver in 30 minutes, right? Then our alternate is that the mu is greater than 30 minutes. So that would be the case that they are not doing what they say, right? So if I were to say, hey, it's less than like 30, that would be me saying, hey, it has to be under it. So here I'm looking for a way what I'm saying that they're not doing what they advertise. So hence it being greater than there. So then my alpha is going to be 0.05 because we're told we want a 5% level of significance there. Okay, so first of all, is this going to be a standard or a student's t? Well, this is a sample, right? So it's going to be a student's t. Right. So student's t. Okay, so now to actually find it out. So our equation for t in this case is x bar minus mu over s divided by rad n. So it's the same E equation as we had earlier, but we have s as opposed to sigma. But we don't, all we currently know is mu and n. We do not have our x bar. So we're going to have to go back to our calculator now. So if we go to our standard deviation calculator, I'm going to want to put all of these things in. All right, so we have 32 minutes, 28 minutes, 21 minutes, 39 minutes, 30 minutes, 27 minutes, 29 minutes, 39 minutes, 32 minutes, 28 minutes, 42 minutes, 35 minutes, 26 minutes, 30 minutes. Okay. All right, so shift 14, yep, okay, we're good. So that tells me my standard deviation and my x bar. So I can say my x bar in this case is 30.57. My standard deviation is 5.88. So let's calculate it out. So let's plug in every one of these little bits into my equation now. My x bar is 30.57 minus my mu is 30. And I want to divide that by 5.88 divided by the square root of, this is 14 is my sample size. And we get 0.3627. And you might get a slightly different value if you round at a different place. You might get a different number than 0.3627. Like you might get 0.3230 or 0.3629. It's fine, right? There's a difference between rounding in different places versus doing it wrong, and I can see that difference when I look at it. So now that we have that t, we need to find our p-value for it. So we're going to go to our, not our z chart this time, but our t chart, because we're doing a t here. So my degrees of freedom, I have a sample size of 14, so my degrees of freedom is going to be 13. So I'm going to go to my 13 row here, and I'm looking for where 0.3627 would end up being on this. So my 0.36 is going to be less than this, so I'm over on this side of that number, right? I would be normally looking for it being in some interval, but this is a fairly close case. So I actually have less than for a one-tail test, right? I have my p-value is greater than 0.25 because I'm to the left-hand side of this here. So all I know about my p-value is that it is greater than 0.250, right? And we don't really care about the specific value purely because we're only looking at it compared to the actual alpha there. If you do care about the exact value, it does end up being like about 0.36 if I remember correctly. So based off of this, do I reject or fail to reject? Well, 0.25 is clearly bigger than 0.05, so I am going to fail to reject. Reject on the 5% level of significance. Since my p-value is greater than my alpha. Again, however you want to say it, it's totally fine. All right, so there is that one. We're on to the back page, our final long problem here. So here we have an x and y value chart here. So this is going to be our chapter 9 stuff, right? Trying to compare the length to the width, and is there a correlation, sorry, the length to the weight, and is there a correlation in the fish that are caught in the lake. So to draw a little scatter diagram of this. Again, this should be a fairly gimme type problem. It's more just to kind of force you to draw it out so that you can look at what the data is looking like. So if we just plot all of these out, looks like my biggest is, I'll do y's up to like 22. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. 2, 4, 6, 8, 10. Okay, and then going horizontally, you probably want to go over to like starting at like 20 to 50-ish. So I'll do a little jump there and say here's 20, here's 30, here's 40, here's 50, here's 60. So again, it doesn't need to be some grandiose graph, but you can get a pretty good estimate there. So I have 22, it's going to be right there. 24, 4, so there's 4, so there's about 24 right about there-ish. 36, 12, so 36, and then 12 is like there. 41, 15, so a little bit past 40, then we're at 15. And then 36, 20, or sorry, 46, 20. So maybe there. So these are fairly clearly going in this direction here, right? Okay. So do you expect your linear correlation and confidence coefficient to be positive, negative, or close to 0? So I'm definitely saying it's going to be positive, right? Because if it's positive, it means that I should have a positive slope on my best fit line. Negative, I should have a negative best fit line. And if it's 0 or close to 0, I'm effectively random. So if this just looked like a bunch of random dots, then that would be close to 0. Spoilers, I'm probably not going to give you one that has near 0 correlation to it. Okay, so I would say positive here. All right, so now we need to compute our x bar, our y bar, our sum of x, or sum of y, or sum of x squared, sum of y squared, and sum of xy. Now I made this small enough that you can do this entire problem by hand. It's not too bad, but again, part of why I had you guys make those calculators is so that you can actually use them. So, pull out your linear correlation calculator. I want to get rid of all of these, get rid of all of these. So my x's are 20, 24, 36, 41, 46. And then my y's are 2, 4, 12, 15, and 20. Okay. So there we go. We don't need to worry about these two things yet because we haven't been asked a question that involves those just yet. So there we go. But if I go to my my worksheet, which is where you guys probably have all of yours, here's all my sum of x through sum of y squared stuff. So that's effectively what I'm kind of being asked here. Also what my x bar is, which I believe my x bar is down here, and my y bar. So x bar ends up being 33.4. Y bar ends up being 10.6. My sum of x from up here is 167. My sum of y ends up being 53. My sum of x squared is 60.69, or it's not 60.69, and then my sum of y squared is 789. And then my sum of x times y ends up being 2103. So there's all those different parts, right? So again, you can do it all by hand, but it is on the work part of your calculator there. Okay, so our next question, if we go down a little bit, sorry, this feels really out of focus, but I can't seem to focus better than it currently is. Sorry. Okay, determine the equation of the least squares line. Well, on our calculator, again, if you did it right, it should give it to you. I'm going to screw over a little bit because I had to zoom in just make it bigger for us. there is that y hat. So our y hat is equal to negative 12.03 plus 0.68x. And again, you can take those out a bit further, like on your work page. You likely have your A and B out to more decimal points, but 2 is more than enough, so we're fine there. All right, then on E, compute the sample correlation coefficient R and the coefficient correlation, the coefficient of D determination R squared. Then explain the mean of the coefficient of determination in the context of the problem. Okay, so our R, again from our calculator, ends up being 0.9962. And our R squared ends up being 0.9924. So what does that mean in context? Well, this tells us, so specifically this tells us the percent of our variation due to our least squares line. So 99.2% of our variation is due to our least squares line, right? Which is good, right? The higher that percentage is, the better your correlation is, and the closer to that line, the best fit your data should end up being, right? And now we have very, very high R and R squareds here because this is almost linear. This is super good data, right? So it's that being high, and all it ever is just it's whatever your R squared is as a percentage. That is the percent of your variation that is due to your least squares line. The other 0.8% here is due to other factors which we do not know or cannot control for. Okay, down to F, we want to compute the standard error of estimate, which is the S sub E. Well, once again, if you made your calculator, you have it right here, right? So 0.7572. Again, you could round it earlier or later, but 4 or 3 is typically a good spot there. Now, for G, if we have a 32-inch northern pike is caught, what would we predict its weight is based off of our least squares line, right? So if I were to just plug that in, right? So if I were to plug 35 in, I would say, let me go back over to this, right? Let's plug it into this. My y hat sub 32, that's a 32-incher, equals negative 12.03 plus 0.68 times 32. Okay, so I would go to my calculator and do negative 12.03 plus 0.68 times 32, and I get 9.73. 9.73 pounds is my prediction, right? So now for my confidence dense interval, and it actually finds this 9.73 in our calculator, but we're looking for a 90% confidence interval for a 32-inch. So I go to this. Here's where I'm going to be using these parts here. So my prediction, I'm doing a 32-incher. Now I need my T sub C, my critical value for it. So I'm going to have to go back to my T chart. And my degrees of freedom here, I only have 5 data points. So my degree of freedom is this minus 2. It's just 3. So degrees of freedom of 3. And I want a 90%. Yes, 90% confidence level. So that's going to be right here. 2.353 is what my T sub C is going to be. So 2.353 353. All right, so then here is my confidence interval for my predicted value there. So that ends up being, my lower bound is 7.6966 pounds. This is my y sub 32. Again, you can just say y, it's fine. And then my upper bound would be 11.6063 pounds. So that would be my prediction for the weight of that northern pike based off of its number of inches, right, from my data there. All right, so that is it. All right. So again, make sure you guys have your note card and that you can do all of these. I am not going to guarantee that it is the exact tests, but it is the very, very similar test. I might change it from known to unknown standard deviation, stuff like that. So do make sure that all of those calculators are working for you and you have all of your notes. With that, good luck. I'll talk to you next time.